Hi, I'm Herb Gross, and welcome once again to our Math as a Second Language video series, where today we're going to discuss converting common fractions into decimals. In my mind, this is an interesting topic because I like the decimal system in terms of conversion factors. In other words, there's something nice about saying, 10 centimeters is a decameter, and 10 decameters is a hectometer, and 10 hectometers is a kilometer, etc. As opposed to, for example, 12 inches to a foot, 3 feet to a yard, 1,760 yards to a mile. You see, all these conversion factors in English are quite complicated. But it's nice to know that you're always trading in 10 of one kind, of one denomination for one of the next denomination. On the other hand, fractions sometimes tell us something that's very confusing to see in terms of decimals. Nevertheless, because decimals seem to be much more visually acceptable to people because it looks like whole number arithmetic, even the stock market in recent years went from listing shares of a stock in terms of eighth of a share and a quarter of a share into using decimals, okay? And so for that reason, it's not a bad idea to know how to convert fractions into decimals. And conversely, as we'll do in our next lecture after this, how you take a decimal which might not make too much intuitive sense to you and convert it into a much more familiar fraction. So with that in mind, let's take a look and see how we can really express fractions in terms of decimals. If you notice, in decimal notation, every fractional part has a denominator that's a power of 10. Now, if you look at 10, the only prime factors it has are 2 and 5, which means that every power of 10 will also have only 2s and 5s. For example, 100 is 10 times 10. That's 2 times 5 times 2 times 5. 1,000 is 10 times 100. Well, 100 is 2 times 5 times 2 times 5. So 1,000 is one more batch of 2 times 5s. And what that tells us is that if the denominator of a fraction in lowest terms contains factors that are only 2s and or 5s, the decimal representation will terminate. Let's take a look at an example. Let's look at 7/8. If you look at 8, it breaks down into 2 times 4. 4 in turn breaks down into 2 times 2. So 8 can be written as 2 times 2 times 2. In other words, its factors are only 2s. The beauty of that is that every time I multiply a 2 by a 5, I'll get a 10. So since there are 3 factors of 2 here, I'll multiply that by 3 factors of 5. You see, that will give me 10 times 10 times 10, or 1,000. To keep the fraction the same, if I multiply by 3 factors of 5 in the denominator, I have to also multiply by 3 factors of 5 in the numerator. 7 times 5 is 35, times 5 is 175, times 5 is 875. So now as a common fraction, 7/8 could also be written as 875 over 1,000. And in decimal notation, since the 1 is followed by 3 zeros, we want to move the decimal point 3 places to the left so that there'll be 3 digits to the right, and we get 0.875, in other words, 875 thousandths. And as a check, we can actually do this. We'll divide 7 by 8. 8 goes into 78 times with the remainder of 6. 8 goes into 67 times with the remainder of 4. 8 goes into 45 times with no remainder. And as I mentioned in an early lecture, we could just keep on going like this. But the tradition is to usually stop after you get a 0 remainder. Now this was nice because the 8 had only 2s as its prime factors. It's interesting, there are very few numbers between 1 and 100 whose common factors just consist of 2s and 5s. In fact, if you want to know what they are, they're 2, 4, 5, 8, 10, 16, 20, 25, 32, 40, 54. No, it can't be 54. 64 and 80, okay? Why couldn't it be 54? What made me realize that? Because 54 is divisible by 3, and if a number is divisible by 3, it certainly doesn't have only 2s and 5s as a common factor. That's another good reason to have a number sense. Here I made what I could call a typo, or whatever it happened to be, but my number sense told me that I had done something wrong here. So look what happens. Let's take a number, we've seen this before. Let's look at 1/3. If I divide 3 into 10, I get 3 with a remainder of 1, 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 and it goes on forever with the 3 just repeating over and over again. Let's see what happens with, say, 2/15. See, 15 breaks down into 3 times 5. The 5 is okay, because what I can do with the 5 is multiply it by 2, and that would turn this into a 10, but there's no whole number I can multiply 3 by to make it into a power of 10. So in other words, this tells me before I even start that when I try to express 2/15 as a decimal, it's never going to come to an end. And let's see if that's true. 15 goes into 20 once with a remainder of 5. I bring down to 0. 15 goes into 50 3 times with a remainder of 5. And look, I've just repeated the remainder. What's going to happen now? I don't even have to do any more. I know that just by seeing over what's happened here, I'm going to keep getting nothing but a sequence of 3s over here. Okay? By the way, I could invent a notation for that. Since the 3 is going to repeat endlessly, I simply put a bar over the 3 to tell me that. The same as with 1/3. It's 0.3 and the 3's repeat endlessly, so I just put a bar over the 3. Let's try it with 1/7. 7 goes into 10 once with a remainder of 3. 7 goes into 34 times with a remainder of 2. 7 goes into 20 twice with a remainder of 6. 7 goes into 80. 7 goes into 68 times with a remainder of 4. This seems to be going on endlessly. Let's see what's happening here. 7 goes into 45 times with a remainder of 5. 7 goes into 50 7 times with a remainder of 1. And now look what's happened. We started with a 1 followed by nothing but zeros. Now we get over to here, and what do we have? A 1 followed by nothing but zeros. And what that means is this whole cycle is just going to keep repeating endlessly. And this is kind of interesting. How could we have known in advance that eventually the cycle would have to just keep on going endlessly? In other words, we know it's going to do that, but how do we know it had to do that before we even did this division? And there's a famous mathematical principle. It sounds almost colloquial. It's called Dedekin's chest of drawers principle. Doesn't sound very mathematically profound. Dedekin's chest of drawers principle. And all it says is, if you have more items than drawers to put them in, then at least one drawer must contain more than one item. Now, what does that mean, for example? Well, let's suppose I had 100 white socks and 100 black socks in a drawer, all scrambled up. And it was dark and I couldn't see. And all I cared was to make sure I got a matched pair. There's 100 white socks, 100 black socks. Okay? I want to pull out enough socks to make sure that I have a matched pair. And the question is, how many socks do I have to pull out? Well, you see, in this case, there's only 2 drawers. And a sock is either black or white. So by the time I pull out 3 socks, I have to have a matched pair. I don't know whether it will be white or whether it will be black, but it has to be a matched pair. Let's see how we can see that. Let's suppose I pick out 2 at random. I could be lucky and have 2 whites or 2 blacks. The worst that can happen in terms of success is I have 1 white and 1 black. So I reach into the drawer and pull out 1 more sock. It has to be either white or black. If it's white, I have a white pair. If it's black, I have a black pair. Notice I'm not saying what color the pair will be. For example, if there's 13 people in a room, 2 of them have to celebrate their birthday in the same month. Why? Because there are only 12 months in a year. So if 13 people each celebrated their birthday in a different month, there'd have to be at least 13 months in a year. You say, well, that's an interesting story. What's that got to do with our 1/7? Well, when you divide a number by 7, how many possible remainders can you have? Imagine you're putting books into a carton, and each carton holds 7 books. And you're going to keep putting the books in till you don't have enough to fill another carton. When that happens, what do you know for sure? There are either no books left over 1, 2, 3, 4, 5, or 6. There can't be 7 left over because then you could have packed another carton of books. So there are 7 possible remainders when you divide a number by 7, which means if you divide 8 different numbers by 7, a remainder has to repeat because there aren't 8 different remainders. So as we write out all these zeros, 0.000000, and we keep dividing, eventually by the time we get to the 8th zero, a remainder has to repeat. Okay? Let's try that with another example. Suppose I look at 2 11s. 11 is a prime number. It's neither 3 nor 5. So I know in advance that when I write this as a decimal, it's eventually going to have to repeat the same cycle of digits endlessly. And the repeating cycle is going to begin no later than the 12th decimal digit because there's only 11 different remainders when I divide by 11. Let's see what happens. I divide the 11 into the 2. The 2 is written as it's 2.0000. 11 goes into 20 once with a remainder of 9. Bring down to 0. 11 goes into 90 8 times with a remainder of 2. Bring down to 0, and look what's happened. The remainder has already repeated. In other words, 2 11ths can be written as 0.18 with the bar over the 8. And by the way, some authors will just do ... And I get very, not upset, but it bothers me a little bit because when you say etc., it has to follow the logical thought of what the person who's writing it has in mind. One of the examples I used to love to give students is I would list the number of days in a month in a non-leap year starting with March. So there's 31 days in March, 30 in April, 31 in May, etc., 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 etc. I would stop before, see this is what, March, April, May, June, July, August, September, October, November, December, January. So the next number I would write, in my mind, would be what? It's the number of days in the month. There's 28 in February. I don't write this. I ask the students, look at this and tell me what number comes next. And they have these very spirited debates as to why it should be 30 or why it should be 31. But you see, I had this crazy notion, which they would have no idea of knowing that I meant by that, I was thinking of the days in a month. See, so by putting the bar over here, I'm no longer saying etc. I'm saying this goes on forever with the cycle 0.18 repeating all the time, okay? So for example, if I write 0.216, but I put a bar over the 216, it's telling me that the cycle 216 starts at the decimal point and goes on forever. If I put the bar only over the 1 and the 6, it tells me that the first decimal digit is 2, and then what happens is the cycle 16 repeats endlessly. So it's 0.2, 16, 16, 16, 16, and the bar over the 1 and the 6 takes the place of me having to write this, especially since even if I wanted to, how can I write forever? Well, I can spell the word forever, and that tells you that it's supposed to go on forever, but I can't write forever, okay? And if I put the bar just over the 6, it stands for what? Only the 6 repeats. You leave the 2 and the 1 alone, and then from that point on, the 6 repeats over and over. Now, this is an interesting part of mathematics. In the real world, we can't measure a number exactly. See, in mathematics, I can say that a piece of string is exactly 6 inches long. In the real world, we'll never know that, believe it or not. Let me show you what I mean by that. I say in mathematics, we can talk about a piece of string that is exactly 6 inches long. In the real world, we would never know for sure. Now, why is that? You say, well, what do you mean I don't know for sure? I put down a piece of string over here. It starts at 0. It ends at 6. It's exactly 6 inches long. Well, you can say that mathematically, but the fact that you can see the 6-inch marking means that it has thickness. Blow this up under a microscope. Where did the 6-inch length end? Was it the beginning of the 6, the middle of the 6, or the end of the 6? And you say, oh, I think it was at the beginning. Okay, now blow the beginning up. Was it the beginning of the beginning, the middle of the beginning, the end of the beginning? In other words, in the real world, eventually They're only terminating decimals because we can't measure more accurately than to a certain number of digits. But this is one of the beauties of mathematics. One thing that takes it beyond the realm of just mere computation. The fact that in the real world, we can't measure to more than a certain number of places doesn't stop the mathematician from talking about what would happen in the real world. Don't poets and writers do the same thing? When Shakespeare writes about Romeo and Juliet, does that mean that that's happening all over the world, or is it a story that's beautiful in its own right? In other words, mathematics is just as beautiful in its own right as Shakespeare is. And this is the reason why even in classical Athens, way back before there was much practical use of mathematics, mathematics was considered to be one of the 7 liberal arts. But let me not ramble on much longer. Let me just go on and show you what I mean by the real world. 1/3 written as a decimal would be exactly 0.3 bar. It wouldn't be 0.3. A lot of people like to leave the bar out. Why is that? 0.3 would be 3/10. And 0.3 bar is 1/3. Let's compare the size of 1/3 and 3/10. We need a common denominator. 1/3 is 10/30. 3/10 is 9/30. Now we have a common denominator. So 0.3 bar exceeds 0.3 by what? 9 from 10 is 1, by 1 part in 30. It means if you could only measure to the nearest tenth of an inch, say, you wouldn't see the difference between 0.3 and 0.3 bar. Guy says, yeah, but what if I could measure to 6 decimal place accuracy? Okay, if this is 6 digits, what fraction would this be? Okay, I'm looking for 1/3. I can't compare these because I need a common denominator, so I'm going to multiply by 1,000. So the numerator here would be 3. I'm multiplying this one by 3, this one by 1,000. I probably should have written one more step in here. I'm comparing 1/3 with a 1 over a 1 followed by 6 zeros. And now to compare these, I have to multiply the 3 by 1,000 and 1,000 by 3. And so the comparison is what? 1,000,000 3 millions versus 999,999 3 millions. And the error is now only 1 part in 300 million. Can you visualize that with a ruler, you're not going to be able to measure anywhere near that closely? So again, you see, it's much easier to look at 1/3 than to try to intellectually visualize what it means by 0.333333 endlessly. So what this brings us to is our summary. And what we've shown today is that when written as a decimal, every common fraction either terminates, and when will that happen? When the denominator has only 2's and or 5's as prime factors, or else it repeats the same cycle of digits endlessly. And an interesting question that will lead into our next lecture is that we've now shown that every fraction, when it's represented by a non-terminating decimal, the decimal will eventually repeat the same cycle of digits endlessly. Intellectually, we want to go in reverse. What if I don't know what the fraction is, but I have a decimal that eventually repeats the same cycle of digits endlessly? Can I be sure that it represents a common fraction? See, be careful. This is the converse of what we just did. For example, it's true that all bears are animals, but it's not true that all animals are bears. In other words, the fact that all fractions can be written as either terminating or repeating decimals does not mean that every repeating decimal represents a common fraction. That's what we'll be dealing with next time. But for now, let's come to our practice problem, which is just another way of saying we've done enough for today. And our practice problem today says round off point. Now, it's a 3, and there's a bar over the 1 and the 8. 0.3, and the 1/8 then goes on endlessly to the nearest millionth. And what you're going to do now is, as usual, pause the video, answer the question, and then come back and look at my commentary. And the reason I give this problem is I mentioned to you that in the real world, we can't measure beyond a certain degree of accuracy. Let's suppose that we're able to measure to the nearest millionth, and somebody tells us, no, you have 0.318181818, it goes on forever. And we want to say, okay, I can't measure that closely, but I can measure to the nearest millionth. So the problem is what? Round off 0.318181818 to the nearest millionth, okay? Well, if we write out what this number says, it's 0.318181818181818. It just goes on forever. But we want it to the nearest millionth. A million ends in 6 zeros. That means we want to look at the sixth column to the right of the decimal point. 1, 2, 3, 4, 5, 6. As a check, what do we have? Tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths. Okay? So we now look at the digit just to the right of the digit in the millionths place. That's an 8. Because that's an 8, we make the digit to its left a 1. And what we're saying is, okay, if I can't measure anything closer than to the nearest millionth, this I might just as well call this 0.318182. Okay? That's all there is to it. We round off. I just want to show you again the beauty of the mathematics, that we cope with things in the real world differently from how we talk about things in the ideal world. And it's talking about what's happening in the ideal world that really helps a student grow beyond the mathematics. What we want them to really learn is not just how to do things, but to understand that by logical thought, you can do things that on the surface looks like they would have been impossible to do. But at any rate, that brings us to the end of today's presentation. I'm looking forward to seeing you all again next time. So stay well, be happy, enjoy. Talk to you later. Bye-bye.